We can apply these concepts to the RC circuit in which we're charging an initially uncharged capacitor. So let's take a look at that. And what I want to do specifically is look at this particular case. I hook up an ideal battery around a capacitor with known capacitance C and a resistance R, and I put in a switch here. I'll assume that I know E naught, C, and R. Notice if this is a real battery, by the time I turn the switch on, the internal resistance I can lump in with this one by the series resistors in series formula. And I want to set things up so that I start my clock, because in this circuit we'll see that the current and in the circuit and the charge on the capacitor varies with time. And I want to set things up so that time t equal to 0 is when I close the switch, and at that instant there is no charge on the capacitor, so it's initially uncharged. When I close the switch, then basically the action of the battery is to pull the positive charge around and put it on this plate, positive Q, and then that induces a negative Q on this plate. And during that time in which it's doing that, there is a current flowing. In general, Q depends on T, and likewise the current depends on time, as we'll see. But we'll apply just our usual KVL to it. It's a DC circuit. The current's always going in one direction. It just varies with time. And we apply KVL in our usual fashion. I'll start at S, go across the EMF, that'll give me a plus E naught. Go across the capacitor, that'll give me Q over C. And the last sign I hit's the negative sign, so a negative. And then I times R, and then the last sign I hit is the negative, and so I'm back to where I started, and so that's my KVL has to be equal to 0. So ultimately I get to this equation from applying KVL to that capacitor, or that RC circuit. I'll rearrange it a little bit to get it kind of in standard form. I'll take the E naught over to this side so it becomes minus E naught, and then multiply through by minus to get this form. And then just divide through by R. Well, I guess I did that later maybe. Then I'll just note here that the current, if Q varies with time, then the current through the circuit is just dq dt. So, and I'll plug that in, and what we get is a differential equation. Differential equations are equations that relate a function, in this case Q of t, and its derivative or derivatives, and that's what we have here. You probably haven't had a course on how to solve these equations. It turns out this one's a pretty easy one, and I'll show you how to solve it, but you'll learn several methods of solving this particular function for the unknown function Q of t, when it has to satisfy that its first derivative, R times its first derivative plus 1 over C times the function back again has to be equal to this constant E naught. Here. I went ahead and divided by R to get it in standard form, and when I divide both sides by R, it goes out here, and we get an R over C times Q of t. And that sets us up pretty nicely insofar as it gives us a constant, R times C. Remember, R is a constant for a given circuit, and so is the capacitance. And it turns out that this constant is usually given a name. It's called the time constant for the circuit. Some people call it the lifetime of the circuit, and sometimes I've seen people use the term relaxation time in this context. But you can look at the units of it. It's very appropriately named. The units of it, just looking at the units of tau, has got to be the units of resistance times the unit of capacitance. This C here is capacitance from up here. Capacitance or resistance is in ohms, but an ohm, remember, is a volt per amp. And capacitance is in farads, but remember, a farad is a coulomb per volt. And so the volts will cancel. The C over here now is coulombs. And an ampere, So those will cancel. An ampere is a coulomb per second, and the coulombs cancel, and the seconds flip over on top. So it's appropriately named. It has units of seconds, so it's obviously somehow related to time. Well, let's solve equation 1, and I'll do it by kind of a standard trick that's called introducing an integrating factor. Uh, but the way people found these things originally was just by looking at this equation long enough up here and just recognizing that if I multiply this whole equation 1 through by e to the t over tau, it becomes this. And then the left-hand side becomes the total derivative of this thing in brackets. And that takes a little thinking perhaps, but it's easier to go back the other way. Certainly if I take the derivative of this product and use the product rule, then I get back up to this form up here, which is where we started. And now then I can just get the indefinite integral of both sides. Both of these are equal, so take the indefinite integral of this side. It's got to be equal to the indefinite integral of this side. And since it's an indefinite integral, one adds a integration constant. Indefinite integral of derivative is just the thing that's in the brackets. And the indefinite integral of e to the t over tau is just the exponential back again times tau. Again, you can differentiate that and you'll find that you'll get to here. And so our general solution to that equation, differential equation, is this, where a is at this point an integration constant. Notice I've also solved this for q by multiplying through by e to the minus t over tau, which gets rid of it here and poses this in that term. And now that I can apply the initial condition is namely at time t equals 0, q of t vanishes. So if I put t equal to 0 up here, this side becomes 0 because that's the charge at time 0. E naught plus a, and e to the 0 of anything is just 1, so this becomes 1. And I can solve this for a. Plugging that back in up here, I get this result. It's got a common factor that I can factor out. And then I can do a little bit of cleanup. This e tau over r, well remember tau, the time constant, is just r times c, and so these r's go out and I get e naught c. And so q of t is just this expression here. One can, once you have q of t, you know that the current is just the first derivative of that, dq dt. And so just plug that in for q and take the derivative and arrive at the current as a function of time. And then it's nice to plot these two functions. Q, I've rewritten it here. It starts off, well, pretty obviously when t is 0, I get 1 minus 1, so it starts off at 0, 0 at the origin. It begins to increase. As it increases in time, this factor gets smaller, and from 1. And ultimately, as t goes to infinity, e to the minus infinity goes to 0. And so it asymptotically approaches this value e naught times c. This term drops out. And I'll denote that by q naught. That's really the final value, the maximum value that the capacitor can have once it's fully charged. Current does something similar. Here's the expression we got for the current. Notice it starts, though, when t is equal to 0 at its maximum value. And t equals 0, I get e naught over r. So that's e naught over r, which is really the highest it gets. And then it falls off exponentially. You can get some interpretation of what this time constant is. It's essentially the time it takes for the current to drop from its initial value, e naught over r, to 1 over e. If I go out here to the time t equal to tau, I can put t equal to tau here, and I'll get rc over rc, so this becomes minus 1, and that becomes this 1 over e. And so at time t equal to tau, the current has dropped from its maximum value to 1 over e of its maximum value. Well, sometimes people like to write those as well. So I've already introduced the maximum Q was Q naught, which was E naught times C. And uh, the maximum current was E naught over R that we see from this plot. So some people then like to write that in terms of E naught over R. And I take the derivative, I find that the voltage drop across the resistor is just this E naught times e to the minus t over RC. Well, to kind of summarize all of this, we get the following set of equations if you followed all of that. In charging a capacitor, the current's maximum value occurs at t equals 0 and then falls off exponentially. The charge on the capacitor plates builds up. It starts off initially at 0 and builds up to its final value, Q naught. The voltage drop across the capacitor at any time t I can write as Q over C. And plugging in this value, I get Q naught over C. But Q naught over C, remember, was just E naught. I've got this value down here. And then the voltage drop across the resistor is I times R, which we found earlier. Well, we'll take a look at using some of those in an example problem, but there's also a number of those example problems in your textbook, so be sure to read the corresponding section that's in the reading assignment for this section, and in particular, be very diligent in going through and working through those example problems.